Hey, John here. Let's talk about lambda expressions and a little bit of the background before we get there as a review of what it means to have a pointer to a function. All right, so let's look at some code I got here. I got a function here, SumFunc, takes two arguments. It prints out hello from SumFunc, and then it prints out the two arguments that has been passed, and it returns the sum of those two arguments. All right, given the code I have here with all this stuff commented out, what is it going to do? It's going to say call direct, colon, and it's going to call SumFunc with 10 and 20 as its arguments. And SumFunc is going to print some more stuff to standard out in a carriage return the sum. And then this guy over here is going to print out the sum and another carriage return. So, as weird as it might be to print a line in the middle of another line, we're going to get two lines of output because ultimately we're going to see two end of lines. Okay. And it's going to say call direct hello from this thing. And then it's going to print out the 30, and then it's going to print another carriage return, right? All right, so let's compile it up and run it. Make sure we're all on board here. So call direct from this guy, and there's my 30, okay? Now let's look and see what's commented out down here. If we undo that and turn it back on, what do we have here? This is how you declare a pointer to a function, okay? You have to have the asterisk has to be bound to the function rather than the type over here, right? This is not a pointer to an integer. This is a pointer to a function. So these parentheses here are required. So the asterisk binds to this guy here instead of the data type over there. All right. And it's a pointer to a function because it has parentheses over here and it has argument types. So that what we're saying here is this is a pointer to a function that takes two integers and returns an integer. You'll notice this is the same function signature as this guy up here. All right. So there's the name of the variable, okay, and I can set fun pointer equal to SumFunc. So this lets me create a pointer to a function. And then once I got a function pointer over here, I can invoke it the same way I would if I just called SumFunc up here, all right? So this is just going to call the same thing a second time by using a pointer this time instead of just directly calling that function, all right? Let's compile it up. Let's run it. So now we got call direct from SumFunc 1020, and then we have call via func pointer, and it says hello from SumFunc, and it works perfectly fine again and still sums them up, all right? So, quick review, we can create a pointer to a function, and that's what this thing looks like. We can assign that pointer a value as long as that value points at a function that matches these data types here, the so-called signature of this function, okay? And once we have a pointer to a function, we can call it just like it was a real one. Let's look at this example. So now we have what we call a higher order function. In particular, that is a function that takes an argument that is itself a pointer to another function. So when we call this function f, it's going to call this other function fp, whose address was passed in. F doesn't even know what it's calling. It just knows it's calling some function that takes two integers as its arguments, and it returns an integer. Therefore, it's okay to return whatever comes back from whatever this thing is, as far as this function f is concerned, right? So he's going to take what? He's got two integers as our arguments for this guy here. That's why fp needs two integers in here, all right? Notice f itself takes one integer as an argument called a, and we're going to pass it to fp here, okay? And then we're going to also pass down a 100. So what's going on? So what do we got? This is the same code we saw before. Call direct SumFunc, create a pointer, point it at the SumFunc, call it again like this. Now what we're going to do is we're going to call f. And f is going to be given our function pointer that we created in a 22. So this line of code down here is going to call this function f with a 22 in a, and then this function here is going to call wherever func pointer is pointing, which is SumFunc, And when it calls that, it's going to give it the A value and the 100. And then some func we already saw is just going to say hello from some func and print itself out and return the sum. When all that's done, the call from F will have printed out this giant message here. And then the return value, which would be what? 122, given this particular example code, and then another new line. So what does that one do? All right. Perfect. I can call a subroutine like F, and I can pass that subroutine a pointer to another subroutine that it then calls indirectly. There's the pointer to the subroutine that I passed as an argument to F, and there it is calling a subroutine using that pointer. Okay. Now, let's make it more interesting. What about this one? Well, the only difference here is, just to drive home the point, look. I'm going to call F, then I'm going to call it again, and I'm going to call it again. All right? Notice what I'm doing here. First time I called it is the same one we just saw. So what I really did here is I just added these two lines of code. All right? So what happens up here? I called F, and I gave it my function pointer, just like before. Here, I'm going to just pass it some func. I don't have to create a pointer variable in main over here in order to pass the value of fun pointer like I did before. I'm just showing you how you could do that if you wanted to. Let's scroll back a little bit here, okay? Now, when I call F the second time, I'm naming some func here directly in here. I'm not saving some func into some fun pointer and then passing the pointer. That's the point here, right? And down here, I want to make it clear that when I call F, F really doesn't know what it's calling. These two calls up here both ultimately called it passing some func one way or another, either by using this variable that has a copy of it or just simply saying, hey, here's some func. This one down here, I'm passing in a completely different function. All right, and you can see the code up here hasn't changed since the last example. So this could either call this function, it could call this one, or any other function anywhere, anytime, as long as it takes two integers and returns an integer. We can pass it anything we want. All right, so we can now run this one. And we get what we would expect. Here's the original example running these two as well as the prior example, okay, with the pointer. Now I'm calling it directly, right? The comment reminds us what we did, okay? And here down here, I called it by giving it a completely different function, again, by directly passing in the address of a function to the function F when I call it here, right? And we can see each time it does whatever the subroutine is that we passed in. So some func, as you recall, adds these two values together. The another func, we'll take another quick look at it. It doesn't add them. This multiplies them. All right? Right? Some func returns the sum. Another func returns the product of the two arguments. So this function up here, this higher order function, we say, calls a subroutine of unknown complexity that does something with these arguments and returns an integer, all right? So F here doesn't have any clue what's going on down here. All right, so let's look at our first Lambda function. First of all, let's take note that the idea of a Lambda expression comes out of what's called functional programming. Different kind of programming. It's based on something called lambda calculus. That's where the name comes from, all right? Now, a lambda function, as we're going to see, is a function that has no name. So one of the things we notice, there's a lambda function right there, or a lambda expression, I should say. It has no name. So quite often it's referred to as an anonymous function. Now, it's kind of hard to call a function that has no name, okay? So for now, I'm going to give it a name. I'm going to create a variable of some unknown type. called sum, another one called mul. The way you read this is the square brackets introduces the lambda. A lambda has a function signature just like anything else, and it has this one. It takes two integers. Okay, here's the body of the function. This is equivalent to the sum func we just saw. All right. It's a function with no name that takes two integers and it returns their sum. Now, this one doesn't print anything out while it does it, but that's what this is going to accomplish. Mul over here is a function with no name that takes two integers and returns the product. Our little function f up here is the same one that was in the last example. It still wants a pointer to a function that takes two integers, returns an int, and it's going to call it, given the parameter passed in here, and 100, just like you saw before, okay? Now, look what happens. If I call f and I give it sum, this is going to do the same thing we just saw. Another one that says mul, again, this is just what we saw before. But now, rather than being forced to actually create a real function up here called sum func and another func, I can just stick it right in my code right here. Okay? So this should be a clue that sum right here, even though I declared it as auto, this variable must have this type right here, or I cannot pass it to this function up here. All right? So the type of a lambda expression like this, and we'll see more complicated kinds in a minute. As long as what we call the capture, the square bracket thing, as long as there's nothing in here, okay, then this whole thing is a function that takes two integers right here. And the value that it returns is whatever kind of value this expression represents inside here. Okay, that's a bit of a leap. But I plus j, if I and j are both integers, well, then clearly this is returning an int. Okay? The compiler automatically decides what the return type is based on what you're returning inside here, all right? Now, if I wanted to, I could obviously cast this to a double or something like that if I wanted to force the type to be something. And there's a way, in more newer versions of C++, there's a way to put a return type in between these parentheses and the bracket. There's fancy schmancy ways of getting around this if it doesn't come out the way you want it. But let's keep it simple for starters, okay? So this is a function that has no name. It's a lambda because it's got these square brackets in here. It takes two integers and it returns an integer because that's what this expression represents in both cases. We can call it, we can pass it to this higher order function just like we did before, and we're writing a lot less code. The whole thing fits on the screen really nice right now, okay? So if we run it, we can see the 122 and the 3300. Quick review. We pass it at 22 for the sum. And it calls what we happen to know as a lambda function over here. It calls the function it's been given, passes in the 22 and the 100, and the lambda returns 100 plus 22, and this guy up here prints it out, okay? When we call mul, we passed it pointer to a function that happens to be a lambda and a 33, so when this guy calls it, it multiplies 100 times 33. Which is why we got that output. Okay, let's look at this one. Same exact function up here. Here's my sum lambda, no change there. I call it, no change here. What's going on here? Well, because C++ and C, it's based on what we call a context-free grammar. In other words, it doesn't matter if I put this lambda into a variable like this and then use the variable right here. I can just as easily have just stuck this entire lambda expression right in there in lieu of the sum. And that's exactly what I did right here. So this code's exactly the same. This is the mul lambda expression. Now, not only is this a lambda expression with no name, it doesn't even have a variable that I assigned it to, okay? That really doesn't have a name, you could say. It sort of does up here in the function f because it gets named as an argument to f, but this function is on its own with no name, all right? And this is, we've known this all along. You can just put any expression you want in place of a variable as long as the type comes out right. Just like I can if I decide to put 30 plus 3 right here as an argument to a function called f, right? This whole thing is the argument list for the function f, right? I can put 30 plus 3 in here just as easily as I can say 33. And I can put an entire lambda expression in here just as easily as I can assign that lambda to a variable and put the variable name in there, okay? All right, and you see you get the exact same results because it really literally is the same exact code. All right, let's look at the next example. All right, so what does this one do? Notice I no longer have the function f defined like this. It doesn't take a pointer to a function anymore because I'm going to use a lambda that's not just a function. We'll see about that in a second. So instead, I'm going to create a template function. These are very similar, but this function here takes a variable whose type is dependent on whatever is passed into the function, right? Like that's what a template really does, right? So down here, I mean, grammatically, whatever FP is has to look like and act as if it can be called like a function, and it has to be able to take a single parameter that is an integer given the way this thing is set up, okay? So that should be some of a clue already where we're going. We're not passing a function to this anymore, okay? Look at this lambda expression down here. It has an I sitting in there, all right? This I is referring to this variable up here. We'll see that in a second. So what is this thing doing here? Very similar to what we just saw, except one of the arguments is in the square brackets. Another argument, j over here, is a regular function argument, and this is going to return I plus j. So I comes in one way, j comes in another way, from a bird's eye view here. But otherwise, it's still returning the sum of I and j. If we look at how we're going to use it down here, we're going to call this f template function. Okay, we're going to pass it sum 1 in the argument of 22. Notice I'm adding one to I here. All right, so let's take a top level view of what's really going on here. I'm going to create a lambda here, and I'm going to call it sum1. Okay, the lambda, when it is created, when the execution comes through here, it is going to capture the value of I, whatever I is in scope, when this assignment is done, which is this I right here. The current value is 1. So the lambda here is going to, as we're going to see, this is actually going to be an object, not a function. What's going to happen here is we're going to construct an instance of a new object whose type is unnamed. And it's going to have an overloaded function that takes an integer. And that overloaded function is going to do this. So how does the I get in there? Think about this for a second. This kind of represents the constructor of that class. The constructor is going to be given the value of I, and that constructor is going to save a copy of the variable I when this lambda is constructed. Later on, when it is used right here, what's passed to f is no longer just a function. This is a class. It's a class instance that has an overloaded operator for a function, all right? And because the instance of that object includes a copy of this I variable that was in scope when this line of code was executed, I will have the value 1, because that's what it was when this line of code was executed. to construct this lambda. We call that capturing I by value. Whatever value it had, here is the value of I when it is executed later. Okay? So when is it executed later? Well, I'm going to call f. I'm going to pass it what is essentially a pointer to an instance of an object. And I'm going to give f at 22. Okay? F is going to treat the object like a function. It's going to invoke the overloaded operator in that function, and it's going to pass it a. So I'm going to call my lambda here, and this 22 is the j. When the lambda runs, it's going to return 22 plus 1. Even though I added 1 over here. I is 2 at this point, but I was captured when I was 1. Okay? So this should print out 23. And so should this one. Okay? Let's run it. And that's exactly what happens. Okay? All right, let's look a little bit more closely what's going on here. Because we capture I by value, okay, we can see we can also do it by reference. We'll get there in a second. We captured the value of I when this was constructed, all right? If we decided to do something cute in here, notice this plus plus I right here. Now the compiler is going to complain because we captured I by value, and it knows that if I'm trying to add 1 to I, it won't really have any side effect. So this is not only superfluous, it's probably broken, because when I grabbed I grabbed it by value, and that suggests that I should be considered a read-only variable. Okay? So let's just try that and make sure that that is the case. Yes, that's exactly what happened. I is a read-only variable. You can't do that in a lambda, okay? So let's put this back the way it was. All right? Okay, I is 1. When it's captured, we can execute it, and we're going to get 23. Even though we already added 1 to I right there. Let's look at the rest of this code down here. What's this going to do? This is the exact same code we have up here, except I said ampersand I. This means capture I by reference. Now I can do this if I want to. When you call f down here and you pass it sum 2, and f up above, the template function calls fp and passes the a variable, which is the 22 right here, right? Okay, because that's the argument here. It's going to execute this code, and it's going to increment the I variable. Then it's going to add on the j, which is the 22. And because it's incrementing the I, and the object holds a reference to the I, it's going to change this variable here when it is called. This is really screwy. So what do we got? I is 1. This doesn't change I in any way. Neither does using it down here. But this does. I becomes 2 right here. We create the lambda here, which doesn't change the I at all. Because all we did is create the lambda object, right, and save it in sum 2. And when this one gets called, and this guy calls fp sub a, then this will get executed and change I to a 3 and add the 22. So the first thing that's going to happen, it's going to print 25, 26, 27. All right? I only do this to make sure we understand the difference between a reference capture and a value capture up here. Okay? Oops. So let's run it again. 23, 23. These are the first ones up at the top. And now we got 25, 6, and 7. All right? Again, close look in here. Capturing I by reference, not by value. Therefore, if we change I in this code here, we're modifying what the reference here refers to, okay, which is the I variable in main. which is why the compiler lets you do this in the first place, as you can tell, because that one didn't work, right? And because why all these other ones keep printing out a number that's one more than the previous one, okay? So what's the point if the whole thing just serves to complicate the death out of everything? Well, let's remember how FindIf works. You should see some theme at this point. Remember what happens if we create a vector, a container of some kind, where you're printing out a container right here, and then I call this print from, and I got a vec. I pass vec in, and what happens? I pass the vec by reference. All right, it's a const reference. And what do? I create an iterator calling FindIf, and I'm looking from begin to end, and I pass it this predicate function over here. The predicate function up here returns true if the value that it is passed in, it starts with a C or a D. Okay? So this code here, what's it going to do? It's going to take this vector here, start at the beginning, and look for the first element that starts with either a C or a D, because that's what the predicate says, and it'll return an iterator to that element. If that is not end, then we found it. If it is equal to end, it's not found, and I print this message here. And whatever is left, I just simply print that out from whatever's found on. Of course, if it's not found at all, it will be equal to end, and therefore this thing is false from the get-go, and it won't print anything out, all right? I guess it'll print a blank line down here, okay? But it will be, because we are looking for things that start with C and D, and you can see there's a C there and a D there. So it should find the C just fine and dandy, and that's what it's going to do when it says print from vec right there, okay? So let's run this, and that's what happened. It scanned through here, finding the first thing that started with a C or a D, and it printed them out. Let's look at this example now. Remember that the predicate can also be an entire class. I hope you're noticing the similarities here, right? Lambdas come in two flavors too. If the lambda does not capture anything, it looks like a function pointer. If the lambda does capture something, it looks a lot like one of these, doesn't it? Notice that the predicate for the FindIf can be an instance of a class that is constructed by this expression right here. This creates a check first character class instance, and it constructs it, and it passes in this ch variable from the print from call. Let's look down here. I call print from and I pass it a C. I call print from and I pass it a E. Okay? So now what do I got? I got this kind of like a parameterized thing. This is a lot like, this is what's happening when you say capture something in a lambda, right? So now what I'm doing is I created an instance of this check first character, and I've given it something for it to capture and hang on to down here, okay? Then later on, when FindIf needs to call a subroutine to evaluate a condition, the predicate condition, it's going to use this object like it's a function, which is going to cause it to call this. And what FindIf does is it passes the value of each element from this to this location as it scans to the container. So it's going to go one at a time from the beginning, all right? Until this predicate function returns a true. So what this thing does is it asks, find me an element that starts with this character. That's why it's called check first character, right? So remember, this one has single characters passed in as an argument, and it has strings in the vector. So this is going to say, print the first one that starts with a C. That would be this one. So you won't see apple, berries. You'll see cherry, daisy, eagle, fox, George, and Hillary come out. And then E will start down here at eagle and just print those out, okay? So let's keep an eyeball on what's happening up here, right? So it's going to return an iterator using FindIf when this predicate function is true, or the predicate object, we could say, is true. And then it's going to print out every element starting at whatever is found, okay? All right, so let's run this one and see what happens. Perfect. Here's the whole list. Here's the first thing that starts with a C. Here's the first one when it starts with an E. Quick review. We have an entire object. We had to create this object. A lot of typing. You'll notice this is much bigger than a lambda expression. You'll notice that everything in here is hard-coded as well. Everything is. All the data types, everything, okay? We have to construct it like this. We can pass in something for it to capture if we want. FindIf, you already know that it needs a predicate function, and when FindIf runs, it passes an argument in to the predicate function, whose value is the value of each of the elements one at a time out of that vector. So you have this notion of capturing something, which is your construction parameter argument here, which is stored there, right? That's how you save a copy of CH into the value member variable, right? So there's your capture. Then you have your function signature would be this. It takes a string, right? This one returns a bool. Okay, all right. We're seeing what's going on here, I hope. All right, so now let's look at the big picture here with Lambda 4. All right, so what's the first thing that leaps out at us? Print from is now a template function. The type of what you get over here is going to be a lambda, okay? It's no longer just a character, because now this iterator, when we call FindIf, the predicate itself is a lambda function that's passed into this template. Everything else is the same down here. It just prints out everything, starting with the first element that was found and returned by FindIf, okay? So let's look and see how this one's created. A lot less code, a little simpler. And you can actually see what's going on right down here in your code instead of looking all over the place at the class that you saw in the last example. We got a vector of strings filled in the same way we saw last time. We print them all out just like we did last time. Then we say print starting from. And what do we got? Well, this is a lambda function because we don't capture anything. Because we're free to change the code in the function itself. This is not necessary for us really to parameterize in order to pass in a C or an E. We just stick the code right here, all right? So we're just writing essentially different predicate functions for each one of these lines of code, all right? Yeah, I suppose if you really wanted to, you could capture something that had the C in it here instead of doing this, and then store it as a variable inside the lambda, which would then be a lambda object that is more complicated than just a function. Okay, yeah, you could do that. But in this case, when it's a simple expression like this, it's very convenient to be able to just put that expression right here like this. And you can change it arbitrarily, okay? And it just works just fine and dandy. All these take a string, and it uses that string to analyze and return a Boolean expression, because that's what you need for FindIf, right? So let's see what that's going to do. Should come as no surprise. There's all of them. There's the first one that starts with a C, first one that starts with an E. This one starts with the first one that's neither an A nor a B, okay? And that's what these three expressions do inside our lambda functions, all right? So these are pretty handy, especially for things like FindIf and other higher order functions that are in the standard template library. There's a lot of things that use predicates or comparators. Okay, quite often you'll see lambda functions used in that scenario. So, thanks for watching. See you next time.